So let's start by quickly recalling what we did last time. So the idea was that you want to estimate the mean of the population, and you are going to do it just by picking a sample from the population and compute the mean over that sample. And then you're hoping that you land somewhere near the true mean of the population. But since it's a random process, the sample means would be random numbers, and you will, every time you pick a sample, you will get a different answer. So the sample means will be distributed in some fashion, and each time you get a different answer, you land here, there, or there. But this much you are assured that they will be distributed about a central value. So the expectation value of the sample mean itself, this is the symbol for the sample mean, and the mean of the sample mean. You look at this distribution and compute the mean of the sample means. This will be equal to the population mean. So you do get some good idea about the population mean, although you have some ignorance. You don't know where you're going to land over here. And this level of ignorance is the standard error, a statistical error in your guess. And this is standard error, which is just the standard deviation of the sample mean distribution.
तो ये इसको गॉसियन कर्व कहते हैं ना?
नहीं, एक सेकंड ठहरे. I just made it Gaussian, something like a Gaussian. You don't know that it should be a Gaussian for now, but for most purposes, it will be a Gaussian. I'm coming to that. Today, in today's lecture, we will be discussing Gaussian in great detail. So there will be, maybe the distribution is different, like that. But whatever the distribution is, there is some, you can have through the formula of standard deviation, you can get an idea of how much uncertainty you have in your guesses. So in practice, you will pick one sample and you get an answer, and you want to have an idea that what are your chances that you will land near the population's mean. So this is what you are assured, that you will be distributed around the population mean. And the standard error which occurs will depend on how big of a sample you pick. Bigger the sample size, smaller is the standard error. And the exact formula is actually also known. So this is some further quantification of this distribution, that the standard deviation of the sample mean distribution depends on how big a sample size you have. The bigger the sample size, the standard error reduces, because the sample size goes into the denominator. And if your distribution itself, your population distribution is spread out, then obviously you expect that your answers, your sample mean will also have a bigger distribution. And you can correct it for finite sizes through this formula. So it's all very intuitive. You have, for population, you have some density, some distribution. you pick, you want to hit the mean over here by picking a sample, your chances depend on two things. One, how distributed the population is, because if it's distributed a lot, you have the chances that you're picking only a finite number, that you might pick from places which are far away from the mean, or maybe a lot from one side compared to the other. Then the mean you will construct will be different from more different from the true mean of the population. Similarly, if you pick more, then you have more chances that you will pick from both sides. And the more you pick, the more you are correctly approximating the mean of the population. So, how distributed is the population and how big a sample you are using? So, apart from these qualitative factors, the distribution of the sample mean, we can say some very concrete things about them, these two. In fact, we can say much more, and you can say that for large enough sample size, the sample mean distribution is normal. By normal, we mean that it's a bell-shaped curve. It's normal, and we know that its center would be same as the center of the population. And this normal curve, there is a specific definition. Well, the usual definition, you can compute it for these normal curves. We know that what would be the standard deviation of this thing. And in fact, the normal curves are completely specified. The normal distribution is completely specified as soon as you just give its center and its width. They all have same shapes. So there's no more to know for a normal curve if you know the mean and the standard deviation. So what we have actually is a very powerful thing, that no matter what the population looks like, population distribution could be like equally distributed like this. So here's the center of the population, and this is something like the standard deviation, or it could be like this. Then here's the mean, and standard deviation is something like this, or it could be even skewed. So here is the center, and distribution is something like this. The deviation is something like this. No matter where you start from, if I pick samples from here, pick samples from here, pick samples from here, compute their mean, and when I will plot the distribution of the mean, the probabilities of means, they will always look like bell-shaped. And I will also know, if I know these parameters for the population, the standard deviation and the mean, then I will also know the distribution of the sample mean exactly, completely. Not exactly, it's approximately normal, but within this approximation, I know it completely. There's nothing more to know. So that's why the sampling from a population is a very, we know a lot about it, that what to expect. But we want to understand this normal distribution much more carefully, because whatever we will do in the course will depend a lot on a good understanding of normal distribution. Although I suppose that this has been taught to you in the previous semester, but I'm just going to go over it again. So have you discussed it in detail in the previous semester? I don't hear an answer. So I will take it as a no.
No, sir.
Really?
Sir discussed both.
You haven't? Yeah, my question was, have you
No.
discussed this in detail in last semester? No?
About the
No,
curve.
sir, we haven't.
Or
No,
you
sir.
have this,
We
well,
just knew that. That's it.
can you say again?
Sir, हमारा
One per. Okay, anyway, so I'm gonna go over it. My understanding is, like, when you do the first course on probability, this part is done in detail, because I think this is part of the syllabus. But let me just go over it again. Yeah, it's a better idea to write in chat. Yes, sir, we did. So some people say it was done, some people say it wasn't. Let me just go over it so that it's a review for some, and for others it will be not in my class. So let me just go over it. And I'm gonna just go in a little bit more detail, so whenever you encounter this distribution, you can recognize it. So Alizen, you can go ahead. Let me take a question from you.
सर वो गलती से बटन दब गया था सॉरी
Okay. Now, let me define this distribution a bit carefully. And we started doing it last time. So we had defined a function which looks like this. And its graph, we quickly argued, is like this. So this function, which I was calling Gaussian, is bell-shaped. And at x equal to 0, its value is exactly 1. So this point is 1 at x is equal to 0. The y-axis is 1. And this thing, this controls the width of this curve. And if I call it x naught, I put this value 1 over under root a is related to this parameter a over here. It controls the width and the exponential behavior. And exponential behavior. There is an exponent, a power of exponent, so it's a decreasing exponential. And whenever you have exponential, things grow very quickly. They grow as a power. Well, not as a power. Exponential growth is a very, very fast growth. But over here, it's an inverse power of exponent. So it's a decrease. And this decrease is exponential decrease, very fast decrease. And if I put this value in, this g of x naught is just e to the power minus 1, which is 0.37. So it has gone down by 66% from its top value. But if I just double this thing, then this is 1 over e to the 4, which is only 0.018. So each time I am just doubling this distance. This is 2x naught, 3x naught. This is e to the 9. So each time I just increase this by this distance, which is this is the scale which controls the width of this thing. Each time I add this factor in where I'm evaluating it, it goes by several powers of e. So this whenever you involve these powers of something, then it goes down very quickly.
Sir,
Yeah.
can you explain how you've gotten e minus 1 where x equals to x naught?
Because I took x naught to be 1 over under root a, and my function was e to the minus a x square. So it's e to the minus a 1 over under root a square, which is just e to the minus 1.
Okay, thank you, sir.
And when I put 2 times under root a's still cancel, and I get 2 square and 3 square, things so and so on. So it's a very fast decrease. Before this point, x is equal to x naught, it's not like if I take this value and double it and then double it, I don't go down so quickly. But apart, further away from this point, this one, as I double, I go down very quickly. So this controls how it goes down. But
So I have a question.
just one moment. But it's never zero. Strictly speaking, it is never zero. Goes down very quickly. So for practical purposes, it just goes to zero, but not strictly speaking. Yeah. You had a question.
Yes, sir, you mentioned about how the A values are actually they're consistent with the width. So I just want to ask that as you're increasing the power of the exponential, the value that you're getting, it's decreasing. So you're moving closer to the center of the bell curve, right?
No. So the values, these values are the values on the x-axis. I'm putting some x. So I put a. I don't know why this thing. Then I put 2a. Well, it wasn't a, it was x naught. 2x naught, 3x naught. And over here, I'm computing whatever the function takes the value on the y-axis.
All right.
So I see where it is over here. What is its value?
Understood.
So now we
And
know.
sir, it will
Hmm.
sir, it will never touch the
Yeah, it will never touch
zero.
zero. Yeah.
Okay.
Now, there are certain properties of this curve. This is a function we call functions curves as well, which are known. Actually, very easy to calculate, but I won't do anything like that over here. But they are, you need to know them because they just the answers, they increase the understanding. So if I take the integral, and what is the integral? Integral is nothing except the area under the curve. So I go from minus infinity to infinity. So I'm counting the total area under this curve, this Gaussian. It turns out that it will be equal to, you can do this integral, and this area is this much. It's just an answer. You can look it up on internet, compute using Wolfram. And if I do this, well, maybe I should write the full function for clarity. I don't know why this is doing it today. This is zero. If I multiply the original Gaussian with x and then compute the integral, this is 0, which makes sense because it makes the function, the integrand odd, and within symmetric limits that's 0. And if I multiply it with an x square, then this is equal to 1 over 2 under root pi over a 1 over a. These are just some answers which will become useful. Now, since the area under this is this much, this gives me an idea. I say, well, let me define a new Gaussian whose area is not under root pi over a, rather its area is 1. So how can I do it? I just multiply it with the inverse of that number. Now when I will find the area under this guy, because in the integral the constants come out, so I know this area was under root pi over a, so they will cancel and I'll get 1. So this thing, you can call it a normalized Gaussian. One whose area is 1. The other,
sir,
yeah.
सर जस्ट फॉर यू टेल यू कि हमने KL2 में पिछली बार सेमेस्टर इंटीग्रेशन नहीं पढ़ी तो आर वी रिक्वायर्ड टू नो
No,
इंटीग्रेशन
you're not integrating. I'm just giving you the answer. All you need to know is, well, you didn't do any integration at all, not even the concept that what integration does.
So we did
No,
some of the
sir.
concept integration, as in some of us already know it, but honestly, हम लोग differentiation पे पहुंचते थे, जब cal पढ़ रहे थे, it was on co-ed first hit, and second cal 2 भी हमने मतलब बस कर लिया sir.
Well, you don't need to integrate anything. Okay, in this course, you don't need to integrate anything. You just need to know what is an integral. So everyone knows that what's an integral. If I have a function, graph of a function, and if I integrate it, I'm actually computing the area under it, right? This much you know.
And when you compute it again, you get the volume.
No, there's no volume over here because everything is one-dimensional. You have x and you have f of x. So if I draw this graph of some function, and these are some points a and b, if I integrate this function from a to b, this is just equal to computing this area, because I'm doing all of this in the paper. So this is the area over this paper. This is this area, shaded area. This everyone, I suppose everyone knows this, right? Can you turn off your mic? Someone's mic is on. So anyone has a problem with this? This is fine? Okay,
Yes, sir.
Okay. So that's all you need to know. And I'm just giving you the answers that this particular function, which is Gaussian, this इसके जो basic integrals हैं, they are like this. And I have just normalized it this way so that its area is 1. So why I wanted to discuss it? I could have started with this Gaussian, this one, whose area under it, the complete area, if you integrate from minus infinity to plus infinity, total area under it is 1. I wanted to do it because sometimes you might encounter like something written like this. And it's not multiplied by this factor, but some other factor. It's still a Gaussian. It's just that its area is not 1. And you can force its area to become 1 by changing this constant. So if in you're dealing with some distribution and it looks like this, as soon as, sorry, there's a minus, as soon as there's a minus here, some positive number here and x square, then it's a Gaussian. But this one has an area 1. Also, the other integrals, let me write how they are changed. I'm going to repeat the integration concept many times, so don't worry. This integral, this is still 0, and this integral, what happens? Only I have just multiplied by a constant. That constant comes out, and the rest of the integral is exactly same as I did before, as I wrote before. Because when you have an integral like this, and you multiply it with a constant, then the constant comes out of the integral. But this gives me an answer equal to 1 over 2a. And this will be important, this answer. So let me just...
Sir,
yeah.
सर थोड़ा सा ऊपर जा सकते हैं एक सेकंड थोड़ा सा सर और
यहाँ पे
जी बस एक सेकंड सर थैंक यू बस
So once I have got a curve whose area under it is equal to 1, it can be a probability density distribution. A curve with area under it, total area under it, area under it equal to 1, can be a probability distribution, probability density distribution. This word is very important. It's slightly different from probability distribution. It's a probability density distribution. So what's a probability density? Again, my assumption is that this was definitely taught last semester, but I'm just going to repeat. This is something you need when you are describing probabilities for a quantity which is continuous, which takes continuous values. So like weights of, you maybe weighing something and it can take continuous values. Length can be take any values. So those kind of variables are continuous variables. And you encounter them a lot. You're looking for price of something, it can take any value depending on how precisely you measure it. So if you have a continuous variable, x over here, it doesn't make any sense to talk about the probability of one specific number, because right next to it, there are more numbers. And if you start assigning each one of them probabilities, you will be assigning so many probabilities that when you add them, they will be infinite. And how will you gonna assign the probabilities anyway? 3.1567, this number will have one probability. Will you give it another probability? So it doesn't make any sense to assign probabilities to continuous variables. So instead, what you do is the following. you make some bins. And suppose x take some value, this variable takes some value x naught over here. So you don't talk about the probability x naught. You say, I'm going to look for what is the probability. So suppose this is the size, small size. Ideally, you want to do it for small sizes, but it's up to you. That what is the probability of finding this value if I do the experiment, if I explore the chance, what is the chance that I will get the for this variable the value x naught, a value between x naught and x naught plus delta x. So a value within this bin. That makes sense because now it makes it a finite interval. So like you can talk about what is the probability of uh, having weight between 2 and 3 grams. You're not saying 2.5, 6, 7, 8, 9 grams, between 2 and 3 grams. So, and to answer these questions, you can define, to assign these probabilities, you can define a curve. You can assign it using a curve, and which you call using a function called probability density. Let's say it's rho of x, it's a function. It takes values depending on x. This is the graph of rho of x. You say that you make these strips. Now this function is not telling you, the value of this function is not telling you what is the probability of being a value x naught. What it tells you instead is that if I make a strip of small width, then this area is equal to the probability of having my variable between x naught and x naught plus delta x naught. So probability of value occurring between x naught and x naught plus delta x in this bin is equal to this area. And what is this area? It's because it's a small strip, so it looks like a rectangle. So it's just the base of the rectangle, which is the size of the bin, times the height, which is just the value of your function at this point. So that's the height, which is the value of your function, and this small base. Similarly, if you want to find the probability of having something over here, you pick the value. Let's say this is.
Sir, can you please repeat
This is
that
x.
again?
Yeah, I'm gonna repeat it again. So if you are finding, if you ask what is the value, what is the probability of having the measurement between x1 and x1 plus delta x within this small range. So you just pick the value of this function at x1 and multiply it with this bin size. So that will give you the probability. So that's the area of the strip.
Excuse me, sir.
G.
Sir, you have x naught plus delta x. What does that mean?
So it's written over here. Probability of value occurring between x naught and x naught plus delta x. So in a small bin. So any value between them is acceptable. You're not saying that if the value is x, what's the probability? You say that within this range delta x, so let's say x naught is 3, and you are saying what is the probability of my value being between 3 and 3.1. So any number between them will be acceptable to you. And you are counting that probability. So any other question?
Sir, the area under the curve would be 1 in probability distribution.
Sorry, excuse me. Area under this curve, under the curve, yeah, I'm gonna come to that. But area of this strip is not 1. Area of this strip is exactly equal to the probability. Which probability? Of the variable being between x0 and x0 plus delta x.
So what do you mean by the bin size?
Bin size is this small length which you have chosen. Bin is like, what is your acceptance? Like you are, because you are not counting probabilities for specific numbers. You are you're counting the probability of a range of numbers. Is the size of the range, this range, these small ranges. And you ideally, at least when you're defining this thing, you want to do it for small ranges. Because the reason I said that it's I can write it like this is because these are rectangles. They won't be rectangle if I make a very big bin size, right? This is not a rectangle. They are rectangle only when I make the bin size small. Now, since it's a probability, so what's the sum of the probability? Total probability. Would be probability of finding them in any bin. This one, this one, this one, this one, this one. So according to rules of probability, you sum over all the rectangles. So that's the total area. So let's write it step by step. Area of all strips. That's just the total area under the curve. And this total area under the curve, well, actually, if you had done a little bit more, well, probably you did it. In calculus, that's how you define the integral. It's just summing up all these small strips. So it's the total area under the curve. But since it's a probability, you know that the total probability by the rules of probability must be 1. So this has to be 1. So you can only use those curves, those functions as probability distribution whose total integral or whose total area under them is equal to 1. That's the reason.
Excuse me, sir, आपने total probability को equate किससे किया है?
Total probability, what would it be? It would be probability of finding them in first bin, second bin, third bin, fourth, 5, 6, 7, 8. So you're counting all the bins. So since the probability of finding in each one of them is one of the strip, so you have to count the area of all the strips. And that's how you do it in the probability. You count, you add the probability of all the possibilities. So when
आपने लिखा क्या हुआ है total probability?
When you add the probability of each bin is the strip. And if you want to find the total probability of finding in any bin, then you have to add the area of all the strips. So that's what I said, area of all the strips. When you add it, you get total area under the curve, right? It would be all this area, all the strips. And that must be equal to 1 if it's a probability. But suppose if you don't want the total area, you want, so here's your variable, here's your curve, defining your probability. You want, first you had small strips, now you have a big range, A to B. And you want to ask what is the probability that my variable, whatever I'm measuring or whatever I'm trying, is between A and B. So suppose there are, these are, for example, weights of some shipments, and you say, what is the probability that is between 5 kg and 50 kg? Now you have a distribution. Maybe there's some weight, some bin around here at 25, which has a less probability than this. But you can count these strips. And when you say that I want the total probability of any shipment between 5 kg and 50 kg, it would be the total area of all these strips between them. And what would that be? That would be just this integral. Because this guy, this gives you one small strip. And this integral sign is nothing except the summation of these strips. So rho x dx is like small strip here, and then you are summing them. This sum, not infinity. Now you have limits where you start and where you end. This is equal to probability of finding x between range A and B. So that's how you deal with continuous variable. And all the variables, you can think of them as continuous and as discrete, both at the same time. I'm going to come to that point in a minute, that how do you, sometimes it's very useful. So like over here, we thought of, sometimes it's very useful to convert discrete variables into a continuous one. Think of them as continuous, because our calculations and our logic which we use become simpler. Now, Basima, you have a question?
Yes, sir, I do. Could you just scroll up for a second for the part where you wrote total probability just there? So you said total probability was something equal to, and I couldn't read the statement, probability of something, then in any bin.
Finding them in any bin.
All right, okay, thank you.
So let me do an example. And this
Sir,
example,
I have a question.
yeah.
Sir, instead of finding the area of a rectangle, would that be, would it be better if we find the area of a trapezium instead? उसका
There's no
फॉर्मूला लगा के
trapezium.
हम ये कर लें,
There's no
क्योंकि
trapezium. What do you mean by trapezium? Oh, well, yeah. So
काफी एरर आएगा.
नहीं, काफी error नहीं आएगा. If I make this delta x very small, then there won't be much error. So if I were doing big deltas, then it won't even be a trapezium. It would be like a curved path. So I don't want to deal with that. So I make these delta x very small. And in the limit when the delta x is going to 0, this is almost exact. And that's what an integral mean. You divide it into very, very small parts. And then when you do the sum, that's equal to the integral. But let's not go into that nitty gritty, because I don't want to make it very theoretical about mathematical points. This maths is just is very important to understand the concept. So the level of maths which I am trying to explain is very important to just understand the concept of when you are given a distribution, what does it mean? Yeah, Basima.
When you, I just want to clarify some terminology. When you're speaking about rectangles, you're talking about strips that are regularly shaped. When you say bin, you mean like a range that's not regularly shaped, right?
No. Bin is just range of x. Rectangle is when I make the strip.
Thank you, sir.
Excuse me, sir. I had a question.
Yeah.
Sir, I lost my internet while you were writing this.
It's all being recorded.
So could you could you still repeat for like 5 minutes?
I
The
can't
one you wrote in blue
5
pen.
minutes for you. I mean, there are so many other people present. You will get it. I'm doing examples and I'm coming back to the same points. You will get it. So let me think, should I do this example? Okay, I'm doing this example. You won't be required to do this kind of calculation in this course. You will not be doing any analytical calculation in the course. All you will be doing is computing means and deviations and argue based on that. But this example is just there to give you some concept that what exactly we are doing. Since many people said that they do not know the concept of probability distribution, so probably it's worth doing. So suppose you have, there's some etymologist and they are collecting beetles. And they have put a lot of beetles in a box. And they only pick beetles of size, minimum size 3. Three centimeter. Now, what happens is that bigger beetles than this are present, but it's very hard to find them. And the bigger the size goes, the probability of finding a bigger beetle goes exponentially down. I'm not saying it's not a bell-shaped curve, it's an exact exponential. And you are told that they decrease exponentially. So the probability distribution is like this. Is 0 if x is less than 3 in the box, because no beetle less than the size 3 was put in the box, so you have 0 chance of finding any beetle of size less than 3. And above size 3, they are given by a decreasing exponential. Like this. So in this is an exponential. I can draw this graph. It's a probability distribution graph. You have the size here, which I'm denoting as x. This is x is equal to 0. At x equal to 3, you have some probability curve starting and going down exponentially. Maybe I can draw like this. And there's nothing over here. So if I pick a bin here of sizes around, let's say, 2 of size 2 and a strip around it, I get 0 because there's no value for rho at that point, that is 0. So when I multiply it by a small bin, I still get a 0. So the probability of finding any beetle of size less than 3 inside the box is 0. But above that,
Excuse me, sir.
yeah.
Sir, I still don't get what you mean by the word bin over here.
Oh, bin is just I pick a value of x and then I make a small range around it. And depending on how much accuracy you want.
Okay, sir, I get it. Okay, thank you.
So now I want, if this is a probability, then I want total probability to be 1. So that will fix this number A. So if you are given a probability which is not normalized, you need to normalize it by hand. So total probability would be what? You start summing bins from 3 up to infinity. And I can do this integral. This integral gives me This is never going to 0 again. And this total probability must be 1 of finding beetle of any size. Now this is equal to,
Sir?
wait, let me just quickly do it. When I put x is equal to infinity over here, that is 0. Minus, when I do this integral, I get this. You don't need to know this integral, but it's a very easy integral. It's just exponential. When you integrate exponential, you get it back, and whatever is multiplying here goes down. And then you put the first limit minus the second limit, which is gives you 3 minus 3. So you are doing a over minus 2, 0 minus 1, which gives you a over 2 is equal to 1. That means a must be selected as 2. So my probability distribution will take this form. If x is less than 3, if x is greater than 3. Now suppose now I ask this question, what is the probability of finding beetles? If I look into the jar and pick a beetle, what is the probability of picking a beetle of size between 5 and 6 centimeter? So now I'm given, there's a full range. This is x is equal to 3. This is the probability distribution. I'm picking this 5 and 6 and saying any beetle between this size. What is the probability? So it's just all summing all these strips. So it's just all this area. So that probability is integrating between 5 and 6, this probability distribution. So I had already done the integral. This gives me minus 2. And when I put the limits, I get e to the minus 6 minus e to the minus 2, which is e to the minus 2 minus e to the minus 6. This number is 0.018 and this number is extremely small, something like that. So I can almost take it 0.018. But the main concept is that you have to do this integral. Or in other words, you have to just find this area under this curve. And you have found the probability of finding a beetle between these two ranges. So any question about it?
Sir? Sir, a power minus 2 into x minus 3 was basically the function of the exponential.
Yeah, exactly. It was the function.
Okay, sir. Okay, sir. And sir, आपने लेकिन plus c नहीं किया?
Huh? Plus c
Like,
when you have limits, then you don't do plus c.
Oh, okay. Yes, you're fine. You're right.
E to the power minus 4. Well, yes, good point. It's e to the power minus 4 and minus 6. Yeah. And I think e to the power minus 4 is 0.018. But whatever that number is, you have to just do this. Now, this idea of using this probability distribution function, you can actually employ it to deal with discrete variables as well. So if you have a discrete probability, then you can, if you have a discrete variable, you can approximate it by a curve and thinking of that curve as a probability density curve. So let me explain it by an example. So suppose, so there's going to be azan here. I'm gonna take like a 2-minute break and you can think about it more. Let me just go up and leave it like this. So I'll be back in 2 minutes. Approximating discrete probabilities by a probability density curve. So suppose you have some discrete variable, like you're looking at number of years of experience, and you are given data only on whole years, like this. And you are given the probability distribution. Since it's given for a discrete data, you will be told exact probability. And I can draw it here like a histogram. The height of this line just tells me what is the probability of picking a guy with experience 2 or 3. So I have drawn the exact probabilities which are given to me. I can think of this discrete variable as continuous as long as I always measure the probability. I can make bins here, like for example, like this. This bin, then this bin, then this bin. So I can make, for example, bins of this size between 1.5 and 2.5, then 2.5 and 3.5. And then I can think of the discrete variable as continuous as long as I always measure the probability in the bins. And I know that when I am talking about this bin, it must be like this guy at 2, because these bins are kind of artificial. Then what I can talk about is that since I have created bins, I have replaced the discrete variable with a continuous variable, but I know that I have to stick to bins so that each bin contains one of the uh, original discrete variable. So then what will happen? Now I can draw a curve, some kind of a curve like that. How do I draw it? Any curve whose area in this bin is equal to this probability. Here's the bin. Here's the next bin. So any curve whose area under the bin is equal to the probability of the discrete variable inside the bin will approximate the discrete probability distribution. So now you can see that what is happening over here. I had discrete probabilities for these numbers 2, 3, 4, 5. They are shown by these specific lines. I say that I'm going to draw a curve so that, and I have first drawn some bins of equal size so that these numbers lie inside those bins. Now I'm going to say that what is the probability of finding the value inside this bin? So that I know that I'm talking about the guy sitting at position 2. So instead of reading this strip's height, I just read this area of the strip. Because when I read the area of the strip, then I'm talking about probability densities. And if I just equate these two, I just choose a curve so that its area under this is equal to the actual probability of finding 2, then the two things will give me same answer. Is it clear? Any question?
So can you please repeat this one more time?
So like let's do it over here. So suppose I want to find the probability of getting the person with experience 8. So that would be, I can do it two ways. I can read this length of this line, whatever this number is. I'm given this number. So it's the probability of having experience 8. Let's say this is number 8A. I have made the bins around it. I want to think of this whole thing as a continuous problem. So I say that I'm gonna look for probability of finding the person, finding the experience inside this bin. Although I know it's going to be the guy with experience 8 only, but I just transform the problem like this. And then since I have made the bin, then it would be the area inside the bin. So I choose a curve so that area of curve inside this specific bin is equal to the probability A of this thing. So what will happen for each bin, I'll be constructing some small strips, some, well, I have drawn it like this way, but more practically speaking, you would be doing like this. Here, 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 here. So this kind of a curve you will be drawing. As long as when you do the area under the curve, it gives you the probabilities which you need. So when you do this, what's the advantage? You can replace the discrete variable with a continuous one.
Sir, the area gives us the probability.
Yeah, which should be equal to the probability which is given by this line, which you already know.
The length of the, okay. Okay.
And actually, if this, if you have chosen a bin of size 1, then since the base is 1, the height will be equal to the height of the function. Because the area you are finding by row of, let's say I'm finding for the 2 times the length of the bin. If I have chosen it to be 1, then row, and this has to be equal to the probability. If I chose the bin size to be 1, then probability is exactly equal to the height of the probability density function. But not if the bin size is different. Like for example, if I'm doing some variable whose values are 2, 2.2, 2.4, 2.6, and so on. So I make bins like this. So now the bin is of size 0.2. And when I draw a function, then that function at this value 2.2 times the bin size 0.2 should be equal to the probability at 2.2. Now that means the height of this function will not be equal to the probability. It will be scaled, but it will be proportional. Depending on how big your bins are, it will be proportional to these heights. Essentially, if you draw these, the shape will be similar of the function which is approximating. It will be just be scaled up or down, but the shape will be exactly same.
Excuse me, sir.
जी,
Sir, changing discrete into continuous, इसका फायदा क्या है?
इसका बहुत ज़्यादा फायदा है because for example जो हमें सबसे ज़्यादा फायदा होगा वो ये होगा कि we will be dealing with the normal curves a lot. And we know the properties of normal curves. We can calculate them, look them up in the charts. But the normal curves are about, it's a concept coming from the continuous variables. While our real life variables are in fact all discrete, if you think about them. So we will be dealing with discrete variables, but converting them, thinking of them as continuous. So always thinking in terms of bins and approximating these probabilities by some probability density, like this curve. So let me go back to the Gaussian. So going back to the Gaussian, I had this thing. And this guy, since I have put this in front, his height is a over pi. And since its area under it is 1, so this is a probability distribution. I can think of it as a probability density distribution. Here's the variable, and this is my distribution, which I'm writing as g tilde of x. What is the mean? If it's a probability distribution, what is the mean? So how do you find the mean? Mean of this variable is just according to our formulas, you are dividing it into bins. So its probability of having it between x and x plus delta x in each bin. And you multiply, you take this value in each of the bin, and you then ask what is the probability of being there. So you multiply it with the probability. And what is and then sum over all possible values of x. So what is the probability? Is given by this probability density multiplied with this small size dx. And then you sum all values of x. So this is like finding this area but with this extra x. So this is this integral. But we found that this integral, when you have an x over here, is 0. So that means the mean of this probability distribution is at 0.
Sir, so whatever is the function, we just multiply it by x and take the integral.
Yeah, exactly.
for mean.
Exactly.
And
For
sir, what will be the upper and lower limits?
lower limit, oh, when I don't write them, they are minus infinity to plus infinity because you want to count all values. What would be the standard deviation? So first, let's find the variance. What would be the variance? Variance, the formula is that you take your values, subtract from it the mean. So you're counting how far from the mean you are, square it, and multiply it with the probability. What is the probability? Probability is you take the probability density function, multiply it with dx, and now you sum over all the possibilities. It's just this. Mean is 0. So it's this integral. I had already computed it before. I have shown you. That's why I had written this value. It's 1 over 2a. So what is standard deviation? It's the under root of variance. So it's 1 over under root 2a. And that's the standard deviation sigma. So if I put, this is standard deviation. So that means that a over there controls the standard deviation. That tells me what is the standard deviation. So I can put this thing from here. I get sigma square is 1 over 2a, and a is equal to 1 over 2 sigma. So let's replace it in our probability distribution. And that becomes 1 over 2 pi, because there was an a up there, and a is 1 over 2 sigma. So it becomes like this. And a is 1 over 2 sigma. So it becomes like this. So this finally is the form of Gaussian which is used. So this factor is there to make the area 1. This gives you, when it's written in this form, x square over 2 sigma square, then this sigma is the standard deviation. But if it's written like some other, like this, then you know that you have to put b equals to 1 over 2 sigma square to find the standard deviation. Then this sigma would just be standard deviation. Also, you can change the mean. You can pick this function. Right now, it's like this. And this sigma tells you what's the standard deviation on one side. Now, I can change it slightly. If I just shift the x by a number, that would mean that this whole graph is shifted. None of the other properties are changed. Just the graph is shifted from x is equal to 0 to x is equal to x naught. All the other shapes and everything else remain same. So this Gaussian, or this normal, is with standard deviation is sigma, and mean is now at x naught. And this is the most general normal distribution you can write. There's nothing else you can do with it. These two properties, that where the center is, where the mean is, and how broad it is. If you increase sigma, it will become like this, fatter. If you decrease sigma, it will become like this. So these two properties completely specify this probability distribution. So any question?
सर ये बुक में कौन सा चैप्टर है?
ये book में he is directly using it. We are on chapter 6 right now. 6 or 7, let me check.
ये नीली वीज की बुक जो है ना उसमें है ये?
मैं वीज में से नहीं पढ़ा रहा, मैं पढ़ा रहा हूँ न्यू बोल्ड में से। ये न्यू बोल्ड का चैप्टर 6 है, but he's using it directly. He's using the normal directly. He has explained it in a previous chapter, in chapter 5, which was not part of our syllabus because you were supposed to have done it up to that point. So if you want to review this, you have to go to chapter 5, but we are actually on chapter 6.
Okay, sir. Thank you so much.
So I'm gonna stop.
Sir, one last thing, sir. Which book should we like mostly use?
New
Bold or
New Bold.
New Bold? Okay.
So I guess I'll try to put some tutorial to do some practice with it, but we don't need integrals. I did this lecture because you at least have to have an idea that what does this distribution, what does normal, and how to compute with normal. Otherwise, you are just using formulas and you have no idea what those formulas mean. Okay, so I'm gonna.
Sir?
I had to say a few more things about the normal, but I think I'll have to say it the next time. Ji.
Sir?
Ji.
Can you hear me? Someone is asking कि अगर आप attendance mark कर रहे हैं?
I am not marking attendance.
Okay, thank you.
Okay, Allah Hafiz.